So we continue to work in section 3.2, and we have a couple of exercises to do to finish things up. So it's good practice for us. The first exercise here I recopied onto a separate sheet. Are these vectors linearly independent? Now, we've already had this kind of problem before. In fact, there are many ways in which many paths you could take to try to show these vectors are independent or dependent. One approach we could take, we could say, is the matrix, let's just say A, with these vectors as columns, 5, 6, -2, -1, -3, 4, 7, 3, 8. Is this matrix invertible? And we could consider those equivalences of the invertible matrix theorem to help us figure this out. If it's invertible, the vectors are independent. If it's non-invertible, the vectors are dependent. Now we have a new way to check this. So let's check the determinant of A. If the determinant of A is 0, the vectors are linearly dependent. If the determinant of A is not 0, then we know the vectors are independent. And so let's see what we can do. Let's calculate this determinant. Now, we got different approaches to calculating the determinant. You could just use cofactor expansion. You could say, I never want to do anything fancy. I just want to use cofactor expansion. I think in this section we've learned ways to avoid cofactor expansion. Here, by the way, I see the second row, those are all multiples of 3. The last row, those are all multiples of 2. So I can do a little bit of cleaning up here. I can factor out a 3. Let's see, I get 2, -1, 1, -2, 4, 8. And then I could factor out a 2 from the last row. And what do I get? -1, 2, 4. I could interchange rows too. I don't know why you would want to do this, but I just want to have at least one example on video where we switch row 1 and, well, 2 rows. So if I interchange 2 rows, -1, 7. Then I have to multiply by -1. So I change the sign of the determinant in that situation. So I now have, what, -6 times something, right? And what I'm going to try to do is I'm just going to try to start putting this in echelon form. Now I've got that -1 up above. I'm not going to worry about it being 1. I'm just going to take row 2 and replace it with row 2 plus 2 times row 1. Row 3, I'm going to replace it with 5 times row 1. So leave that alone. And then I get 0 here. And now I'm adding 2 times row 1, 2. So I get 3. 2 times 4 is 8, plus 1 is 9. And then I'm adding 5 times row 1 to row 3. 5 times 2 is 10, minus 1 is 9. 5 times 4 is 20, plus 7 is 27. Okay. Okay, now actually I see something that I see two rows being proportional to each other. Now that's not so obvious. So what I'm going to do is I'm just going to factor out a 3 from the third row. Actually, you probably want to factor out a 9. I'm going to factor out a 9 from the third row and a 3 from the second row. So I'll do two things. It's kind of more than I have to do, but maybe that's the easiest way to see this. So I factored out a 3 from the second row, a 9 from the third row, and notice I have two identical rows. So you don't have to notice this, but as soon as you notice that you have two identical rows, the determinant has to equal to 0. So this is stuff times 0, which is 0. The determinant of this, our original matrix is 0. So now if we go back, we can say since determinant of A is 0, the vectors are linearly dependent. They are not independent in this problem. That's a nice little problem. So there are many ways you could have gotten at the determinant here. I just sort of tried to throw everything in there just to give us some more exposure to some of these shortcuts. But the two identical rows was just great, because once you see that, you know your determinant's definitely 0. So the original vectors were dependent. We got one more exercise I think we can do in the same video here. This is not hard. It's just meant to be an observation here. So first in A, I want you to compute both AB and BA. Okay, so that should be like, yeah, ask us to multiply two matrices on the final exam, please. So let's see what AB turns out to be here, going across first row. First column, I think I get 0. First row, second column, I think I get 2. First row, third column, 2 plus 2 is 4. Second row, first column, I think I get 1. Second row, second column, 0 plus 2 plus 0. Second row, third column, 6 plus 0 plus 0. Okay, last row, first column, 0. Last row, second column, I think we get 1. Last row, third column, I get -2 plus 1, I think I get -1. Okay, BA, we would expect this by now to probably be different from AB. Okay, here I go. I get -2. Ooh, I like this first row. First row, a 0, 2. Now second row, first column, I get 1 plus 6 is 7. I get 2. I get 2 plus 0 plus 0. Third row, first column, I get 2. Third row, second column, I get 1. Third row, third column, I get 1. Okay. Now, so these are different, of course. Now let's compute the determinants of both of these. And there are lots of ways we could do this. We could even compute the determinant of A and B separately and just multiply them using this theorem we just saw, right? Because the determinant of AB is going to be the determinant of A times the determinant of B. But since I have AB here, I'm actually just going to use the matrix I have right here, because I'm noticing here it's easy to expand down that first column, plus, minus, plus. So I'm going to get 1 times a negative 1 times a 2 by 2 minor, removing that row and column, 2, 4, 1, negative 1, 2, 4, 1, negative 1. And that's it. So I'm going to have negative 1 times negative 2 minus 4. So I think I get 6 for the determinant of AB. The determinant of BA, I'm going to calculate from this BA matrix also. And I'm going to expand. I'm going to use that 0. Maybe I'll go across the first row. So we have negative 2 times plus 1 times a 2 by 2, 2, 2, 1, 1, plus 0, plus 2 times, so it's plus minus plus, so that'll be a plus 1. Cross out its row and column, 7, 2, what was it? I think that was a 2, right? 2, 1. Let me just make sure. So third row, first column. Yeah, that was a 2. So I have 2 minus 2 is 0 here. This is going to be 0 plus 0 plus 2 times 7 minus 4 is 6. Of course, these come out the same, right? So it's kind of interesting that because the determinant of the product, of course, because determinant of AB is determinant of A times the determinant of B, we could have calculated these separately. And notice that once you take these apart and write them as determinant of A times determinant of B, sorry, slipped down there, I can now commute these because these are just numbers. Numbers can be commuted. So the determinant of A times the determinant of B is equal to determinant of B times the determinant of A. I don't think I'm going to go through another calculation because this has gone on long enough. But it's just sort of interesting that that determinant gets preserved even though when you multiply in two different orders, you get different results for AB and BA. I don't know, there's something just intrigues me about that. So that's the end of our 3.2 lectures.